We've been talking about gases. Now we're going to talk about mixtures of gases. Just like we use solutions, which are mixtures, gases are often mixtures as well. So a good example of a gas mixture is air, right? So there's air in this room, we're all breathing it. Here we're talking about dry air. What's the difference between something that's dry and wet? Not a trick question.
One's wet and one.
What is it wet with? Water.
Oh.
So dry air would not have any water in it. That would be 0% humidity. And the reason that we say dry air is because, well, that is a specific thing, whereas if you've got water in it, that humidity is going to vary a lot. And so just for comparison's sake, we're going to talk about dry air. So in air, we've got a mixture of nitrogen and oxygen gases. Those are the two main gases. There's a little bit of argon, a little bit of carbon dioxide. So this table is showing us the percent by volume. So in, say, 100 liters of air, there would be 78 liters of nitrogen and 21 liters of oxygen, 0.9 liters of argon, and 0.04 liters of carbon dioxide. There are, of course, other gases. A good example today is there was kind of a smell of natural gas over there. So we could add in that sulfur-containing compound that they put into natural gas to make it smell so bad. So that's been floating around. Of course, there's lots of other things that can be in the air as well. Come on, advance the slide. So sometimes we can think of a gas mixture as though it were a single gas. So we talk about air as if it was a single gas. We can measure the pressure, the volume, and the temperature of a sample of air as if it were a pure substance. We can use the ideal gas law and calculate the moles of gas particles or molecules in that sample, even though they're different molecules. Because the volume, the volume is dependent on the number of particles, not on what they are. The gases within the mixture behave independently. So say, we've got a box of air. The nitrogen in that sample is going to behave as if it were the only gas in the box. It's going to fill the whole space and exert a pressure on the walls. The oxygen is going to act as if it's the only gas. And this is because gas particles are very far away from each other and they don't interact with each other. So they act as if they're the only thing in there. So a single gas in a mixture of gases is going to exert a pressure. That is not the total pressure, but that's part of the pressure. So it's a partial pressure from one of the gases. And so we can use the ideal gas law to calculate that. We can rearrange the ideal gas law and get that the pressure is equal to the number of moles of that gas times R times the temperature divided by the volume. So each of the gases in the mixture is exerting a pressure that is equal to the moles of that gas times R times T divided by V. Dalton's law of partial pressures tells us that the sum of all the pressures is equal to the total pressure. So, say you've got nitrogen and oxygen in this sample. The nitrogen is exerting a pressure. The oxygen is exerting a pressure. The total pressure is the sum of the pressures from each gas. So the total pressure will be the pressure from gas A plus gas B plus gas C. Any questions yet? So here we're doing a little math. I'm not going to make you derive this, but let's just look at how it works. So P total, like we just learned, is the sum of the pressures from each individual gas. And we learned that the pressure from an individual gas is the number of moles of that gas times RT over V. So the pressure from B, gas B, is the number of moles of gas B times RT over V, etc. If all of these gases are in the same sample, they're mixed together, then their temperatures are all the same and their volumes are the same. And of course, R is always the same. So we can factor out RT over V, and we get here the sum of the moles of the gases times RT over V. So here what we're saying is the total pressure is equal to the total number of moles of gas times RT over V. It doesn't matter that they're different gases. Any questions? If we take the pressure of one of the gases and divide it by the total pressure, this is the kind of thing we do when we're doing a percent, right? We look at part of it divided by the whole thing, and then we multiply by 100. So part of the partial pressure gas divided by the total pressure gas. So that is a ratio, and the partial pressure of A is equal to NA times RT over V. The total pressure is equal to the total number of moles times RT over V. The RT over V's cancel out. And we get the moles of A divided by the total number of moles. So this has a name. This is called the mole fraction. If we multiply the mole fraction by 100, then we get mole percent. So this is just mole percent before we multiply by 100. So it's the moles of gas we're interested in divided by the total number of moles. And I guess you could call this the pressure fraction. So this mole fraction is the chi A here. That's a weird X, that's a Greek letter chi. So mole fraction is equal to the moles of the one gas divided by the total number of moles. And then you can look at this and rearrange things around and end up with this little guy down here. If we want to know the pressure of one of the gases, the partial pressure, that will be equal to the mole fraction times the total pressure. So this is like using a percent, right? If one of the gases is 50%, then its pressure will be 50% of the pressure. This is the mole fraction. To do that problem, we take 50% and divide by 100 to get 0.5. That's equivalent to the mole fraction times the total pressure. So partial pressure of a component of gas in a mixture is its mole fraction times the total pressure. The mole fraction is equivalent to the percent by volume. So let's just go back to this slide real quick. Here we've got 78% by volume. That is going to give us the mole fraction. So that's a percent. The mole fraction for N2 is going to be equal to 0.78. The mole fraction for oxygen is equal to 0.21.
These are constants, this is all the time?
This is in air, just
Only air?
regular air. If we have look at the mole fraction of argon, that's gonna be 0.009. Okay, so the mass percent, the volume percent is really just the mole fraction times 100. So if we know that nitrogen is 78% of the air, we can find the pressure of nitrogen by taking the mole fraction of nitrogen and multiplying by the total pressure. So currently in the room, we have a partial pressure from nitrogen of 0.78 atmospheres. And the partial pressure of oxygen would be 0.21 atmospheres. Any questions? So here's an example. It's kind of an annoying example, but we're going to do it. To prevent the presence of air, noble gases are placed over highly reactive chemicals to act as inert blanketing gases. A chemical engineer places a mixture of noble gases consisting of 5.5 grams of helium, 15 grams of neon, and 35 grams of krypton in a piston cylinder assembly at STP. Calculate the partial pressure of each gas. So we don't deal with things in real life that are this reactive. You know, we deal with things where, well, we need to put it in a closed container because it's going to dry out or something. But this is, even if you put it in a closed container, if there's any air in there, this is going to react with it. How do we keep it from reacting? Well, one way is to flush the container with gases that it doesn't react with. So that's what they're talking about here. So they're giving us a bunch of numbers. Mass of helium, mass of neon, mass of krypton. And they want partial pressure of each gas. Well, what is the partial pressure of each gas? Is there an equation that relates partial pressure to other things?
The one we just did, right?
The one we just did. I honestly
I just don't
do
remember.
not expect you to remember it. The partial pressure of gas A is going to equal to the mole fraction of A times the total pressure.
And we do not have to memorize this.
No. So what we need then is we need the total pressure and we need the mole fraction. Well, what is the pressure of this gas?
All of those together.
Well, yes, but how can we find out what the total pressure is if we don't know what the partial pressures are?
You turn those grams to moles.
What does this mean at STP?
Oh, we have to use the ideal gas.
STP means standard temperature and pressure. What's standard pressure? 1 atmosphere. So the 3 letters there are telling us what the pressure is. So from that, from STP, we recognize that the pressure, the total pressure, is equal to 1 atmosphere. And we could say that that's exactly 1 atmosphere. Okay? So that's our total pressure. We need mole fraction. We have masses. How would we go about calculating the mole fraction?
Now do you count grams to moles?
Now we're going to use grams to moles.
He said I knew it was coming.
It's in there somewhere. So the mole fraction of A is going to equal the moles of A divided by the total number of moles. So to find the moles of A, we're going to take the mass of A and convert it to moles. So we've got 5.50 grams of helium. And I want to convert that to moles of helium. So I'm going to divide by grams, so the units cancel out. Got my units in place, I go to the periodic table. Helium is 4.003. Oops. 5.5 divided by 4.003. 1.3739 moles. Well, so if we're finding the mole fraction of helium, that's the moles of helium, but we need the total number of moles. So we have to do this to all of them and add them together. So 15 grams of neon. It's a little tedious, but you know, at least we're just doing the same thing and not having to come up with new things. So mass of neon, 20.18. I guess I should put ones in there. So 15 divided by 20.18, 0.74331 moles. So this is moles of helium. This is moles of neon. And then 35 grams of krypton. Krypton is 83.80. So that's moles of krypton. So we're going to add all these together to get the total moles. So I'm just going to, we're adding all those together. So I got 2.53494. Okay, so now we can calculate mole fractions. So mole fraction of helium is the number of moles of helium divided by the total number of moles the unit mole cancels out. I'm going to round this to 2 sig figs at this point because I'm going to get rid of that because we really don't need that. So mole fraction of neon, 0.74331 moles, divided by 2.5349 moles. Oh, shush. Let's start that one completely over. Mole fraction. I think that did much good. Krypton. 0.41766 moles divided by 2.5349 moles. 0.165. I'm gonna erase this. So the partial pressure of helium equals the mole fraction of helium times the total pressure, which is 1 atmosphere. So that's going to give me 0.542 atmospheres. Because the total pressure here is 1, the partial pressure of each of the gases is equal to their mole fraction, because we're just multiplying by 1. So that's for helium. There's just not enough room here. The pressure of neon will be 0.293 atmospheres. And the pressure of krypton, 0.165 atmospheres. That is a super tedious question. And also something we don't do very often at all. Why do we care? I don't know about this one. Any questions? Gas mixture contains an equal number of moles of helium and neon. The total pressure of the mixture is 3 atmospheres. What are the partial pressures of helium and neon? Well, if they are equal number of moles, what would the mole fraction of each be? I'm hearing these. Well, it's 1 helium to 1 neon, but the partial pressure, the mole fraction is the moles of helium divided by the total number of moles. It's very much like the percentage. So if we have half one and half the other, the mole fraction is going to be half, or 0.5. Right? Equal number would be 50%, 50%. So they're 0.5, 0.5. So then the partial pressure is going to be their mole fraction times the total pressure. So which choice is correct? C. So that was probably a harder way of thinking about it. The other way you could think about it is, well, if there are equal number of moles of each, then the pressures must be the same. And here, with limited choices, this is the only one where the pressures are the same. Questions? A sample of hydrogen gas is mixed with water vapor. The mixture has a total pressure of 755 torr, and the water vapor has a partial pressure of 24 torr. What amount in moles of hydrogen gas is contained in 1.55 liters of this mixture at 298 Kelvin? Well, let's highlight the numbers. And highlight what they're asking for. We want moles of hydrogen gas. So we have a couple of pressures here, 755 torr. That is a pressure. Is that the total pressure or a partial pressure? What is that? That's the total pressure. So I'm going to put a T there. And then we have another pressure that's 24 torr, and it says that's the partial pressure of water. So that's the pressure of just the water. And then we have a volume of 1.55 liters and a temperature of 298 Kelvin. So the total pressure here, what are the two gases that are in this sample? We've got hydrogen mixed with water. So the total pressure is going to be the partial pressure of the hydrogen plus the partial pressure of the water. If we use the total pressure to calculate the moles, we'll get the moles of hydrogen and water, but we want just the hydrogen. So that means we want to use just the pressure of the hydrogen. So how could I find the partial pressure of hydrogen? Subtract. So I'm going to take the total pressure and I'm going to subtract this partial pressure. Do that down here. So the partial pressure of H2 is going to be 755 torr minus 24 torr. $731 torr. We want to use the pressure of the hydrogen because we want the moles of the hydrogen. So what equation are we going to use to calculate the moles? Yeah, the PV equals nRT, right? So if I rearrange that, I'll have the number of moles of hydrogen is equal to the pressure of hydrogen times the volume divided by R times the temperature. The volume and the temperature apply to both of the gases. Well, is torr a good unit for the ideal gas law? No. Need to convert it to atmospheres. 1 atmosphere is 760 torr. So 731 divided by 760. 0.96184 atmospheres. Okay, I'm getting a little rowdy next door. 6184 atmospheres times the volume divided by R. It's the ideal gas constant, 0.08206 liter atmospheres per mole Kelvin, times the temperature, which is 298 Kelvin. Again, be careful doing this on your calculator because this is the sort of problem people mess up a lot. So 0.96184 times 1.55 divided by the quantity, open parentheses, 0.08206 times 298, close the parentheses, equals 0.060966 moles. So what would I round that to? I need 3 sig figs, so what's that going to be?
0.0610.
So I'm keeping this place 1, 2, 3, 4. The 6 causes the 9 to round up to a 10, but I need to keep the 0 there. So this is my moles of hydrogen. questions? Yes.
Why would it be 3 sick pigs? Because there's the 24 tour.
Good question. There is a 24 tour. The 24 tour is subtracted from the 755, and when we subtract, we're counting decimal places. And so this number still has 3. It's a great question. Any other questions? So at the beginning of the chapter, we talked a little bit about diving. If a diver's breathing compressed air, then you'll get an abnormally high partial pressure of oxygen in the lungs, because the air is pressurized, and the partial pressure of oxygen depends on the total pressure. Well, too much oxygen is not good for you. So this is, everything is toxic in certain amounts, right? Water is toxic if you get too much. But if you don't have any, that's bad also, right? Oxygen, if you don't have any, you're going to die. But if you get too much, also going to die. So, I guess you could say nothing is safe. Or you could say everything is safe at some level. It might be super, super small. So this is air at the surface. 0.21 is the partial pressure of air. When we get down below that, we get into what's called hypoxia. Hypo meaning below. So here we have not enough oxygen. There's a fair range here that is safe, but then you get up here past 1.6 atmospheres, and now you're getting too much oxygen, and that's oxygen toxicity. So a diver breathing compressed air, it can only be compressed to a certain amount before it becomes dangerous for them. There's also nitrogen in air. Compressed air also has a higher partial pressure of nitrogen. And if we get nitrogen above 4 atmospheres, that can cause what's called nitrogen narcosis, or rapture of the deep. You're like, well, that doesn't sound bad. With symptoms similar to alcohol intoxication. Yeah, people do that for fun, right? Yeah, but here you are, meters and meters and meters below the surface of the water, depending on this tank of compressed gas to breathe. And you need to stay away from sharks. And there's things that could happen down there. There's a reason that most of us don't go down there. No, thank you. So, get too much nitrogen, you're not going to be able to think clearly, and that's very bad. So, to avoid the problems of nitrogen narcosis and oxygen toxicity, deep sea divers will breathe specialized mixtures. So, heliox, as the name suggests, is a mixture of helium and oxygen gases. What happens if you breathe too much helium? Your voice gets really high and squeaky, right? Well, you can't hear each other down there anyway. That doesn't matter. As long as you're getting enough oxygen with the helium, you're fine. Now, if you're breathing only helium, you'd suffocate, right? So they're going to mix helium and oxygen, and then we can avoid getting too much nitrogen. Let's see what's on the next slide. So the heliox would not be appropriate to breathe higher up, because you're not going to be getting enough oxygen. So what they usually do is you have 2 tanks, a tank of compressed air and a tank of heliox. And as you descend and ascend, you change the ratio of gases that you're breathing. That sounds complicated. There's a reason that you have to take all those classes and get certified before you can go scuba diving. So a diver breathes a heliox mixture with an oxygen mole fraction of 0.050. What must the total pressure be for the partial pressure of oxygen to be 0.21 atmospheres? So we're looking for the total pressure. So we talked about, I'm not going to say we learned, but we talked about an equation that relates these things. The partial pressure of oxygen is going to be equal to the mole fraction of oxygen times the total pressure. So what have they given us here? Well, oxygen mole fraction is 0.050. And we want the partial pressure of oxygen to be 0.21 atmospheres. Because that's what we have at sea level. This is what we're used to. So we're going to take this equation and we're going to rearrange. We're going to solve for P total, divide by mole fraction of oxygen. And those will cancel out. And so the total pressure needs to be the partial pressure divided by the mole fraction. Or 4.2 atmospheres. Any questions? When we have chemical reactions that generate gases and we want to collect the gases, this can be a little bit tricky because if you don't have a containment system, they just float into the air and spread out all over the place. So this is one way of collecting gases. It's called collecting a gas over water. Probably be better to say collecting it through water, but whatever. So here in this test tube, we have zinc and hydrochloric acid, and those are reacting together and generating hydrogen gas. The hydrogen gas is going to build up a pressure and it's trying to escape. And so it's going to go through this tube where we have directed it down through some water and up into an overturned beaker. So this beaker was originally full to the top with water. There was no air, there's no space up there. But as the hydrogen is generated, it's going to fill this space and displace the water. Okay? Now, we've got water here. The hydrogen is over the water. The water is going to be evaporating. So there will be some water molecules in here as well. This is not going to be dry hydrogen. This is going to be wet hydrogen. The partial pressure of the water vapor, which we usually call its vapor pressure, depends only on the temperature. Because, I mean, how would you measure it, right? That would be tricky. So this is very convenient. The vapor pressure of water depends on the temperature. As the temperature increases, the vapor pressure increases. So in this sample where we're collecting this hydrogen, if we know the temperature, then we can look up the vapor pressure of water. And we can measure the total pressure. The best way to do that is just to get the level of water inside and outside to be the same, and then we know that the pressure is the same as outside, which we can read from a barometer. And then we have to subtract the water vapor pressure. So we look that up in a table, and we're going to subtract it from the total pressure. Okay, so here's an example. A sample of acetylene is collected over water. The total gas pressure is 738 torr, and the volume is 523 milliliters. At the temperature of the gas, 23 degrees Celsius, the vapor pressure of water is 21 torr. How many grams of acetylene are collected? And so many words. let's focus on the numbers. There's all my numbers. And my question is, we're looking for grams of acetylene. We don't have a gas equation that gives us grams, do we? But we do have an equation that gives us moles. And we know how to convert from moles to grams. So the first thing we're going to do is we're going to calculate the moles of acetylene in this, whatever it is, collection vessel. So I'm going to write these numbers down. I've got 738 torr. That is the total pressure. And then I've got a volume of 523 milliliters. And I have a temperature of 23 degrees Celsius. And I have the vapor pressure of water. The partial pressure of water is 21 torr at this temperature. So I am trying to find the moles of acetylene. The moles of acetylene, C2H2, from the ideal gas law is going to be the partial pressure of the acetylene times the volume divided by R and the temperature. The volume and temperature of the water vapor and the acetylene are the same, but the pressures are not the same. We have the total pressure, which is the sum of the pressure from acetylene and the pressure from water, and here we have the pressure of the water. So to get the pressure of the acetylene, we're going to need to subtract. So the pressure of just the acetylene is going to equal the total pressure minus the partial pressure, or the vapor pressure of water. So 738 minus 21. Is torr a good unit for the ideal gas law? No. Need to convert this to atmospheres. Atmospheres. Okay, so that's the pressure I'm going to use. How are the units on my other quantities? Volume's not good, is it?
No, temperature either.
Not the temperature either. So let's call this 523 times 10 to the minus 3 liters. And we're going to have to convert this to Kelvin. I'm going to add 273, so I'm going to get a Kelvin temperature of 296 Kelvin. So my pressure times my volume divided by R 0.08206 liter atmospheres per mole Kelvin times the temperature 296 Kelvin. Atmospheres cancel, liters cancel, Kelvins cancel. So what we end up with for units there, in the units, we have 1 over moles, which is equal to moles. Because when you divide by a fraction, that's the same as multiplying by the reciprocal of the fraction. You can just say, I believe you. It's fine. Okay. So my pressure times my volume. Zero point 0.02013 moles of C2H2. Are we done? We gotta get to grams. We're not quite done. So I'm running out of space down there, so I'm gonna move up here. I'm gonna need the molar mass of acetylene, which I get from the formula. .036. So I'll take my moles. And I'm going to multiply by grams and divide by moles. So it'll be 26.086. Except that wasn't, it's not an 8, that's supposed to be a 3. Yeah, I screwed that up. Anybody get that number? Because I've done it twice and I've gotten 2 different answers. So I'm going to do it again.
I got your answer.
You got it? Okay. That's 2 out of 3. So we should report that answer as 0.529 grams. Any questions? What do you say we skip that one? Yeah. It's just very much like the one we just did. So let's skip that one. Oh, what the problem is here? Oh, well, actually, that's the last slide. And we've got 15 minutes left, so we'll do it, and we'll still get done early. Okay. A common way to make hydrogen gas in the lab is to place a metal such as zinc in hydrochloric acid. The hydrochloric acid reacts with the metal to produce hydrogen gas, which is then collected over water. Suppose a student carries out this reaction and collects a total of 154.4 milliliters of gas at a pressure of 742 millimeters of mercury and a temperature of 25 degrees Celsius. What mass of hydrogen gas in milligrams does the student collect? So we have a volume, a pressure, and a temperature. And we're looking for hydrogen in milligrams. So like the previous problem, we can use the ideal gas law to calculate the moles of hydrogen and then use the molar mass to go to grams. So I've got some numbers over here, 154.4 milliliters. My volume, got 742 millimeters of mercury. That's pressure, 25 degrees Celsius is my temperature. So the moles of hydrogen, we're rearranging it PV over RT again. So there's problems like this on the chapter 6 worksheet, and students get them wrong a lot. There's 3 words that are very important in here. Collected over water. The previous problem, now I'm seeing why this problem's in here. The previous problem, they told us what the vapor pressure of water was and said it was a mixture of acetylene and water vapor. This one doesn't mention the water except for collected over water. Anytime you have a gas collected over water, you need to find the partial pressure of water and subtract it from the total pressure. So the pressure over here, that's the total pressure, and I want this to be the partial pressure of hydrogen. Well, I don't know what the partial pressure of water is at that temperature. We're going to go look it up. So the temperature is 25. So we can go to a table like this. At 25 degrees Celsius, the vapor pressure of water is 23.78 millimeters of mercury. 23.78. So pH2O equals 23.78. So that's H2O. The partial pressure for the water then is the total pressure minus the partial pressure of water. So 742 minus 23.78, 718.22 millimeters of mercury. And we need that to be in atmospheres. So 1 atmosphere is 760 millimeters of mercury. That's why I said you're probably going to memorize the 760 part, because we just do this like all the time. So there's my pressure of hydrogen. And then I need the volume. Well, the volume's given in milliliters. 154.4. Milli stands for times 10 to the minus 3 liters. There's our gas constant. And then for the temperature, we need to convert that to kelvins. So 298 kelvins. Zero 0.00596668 moles. And that's moles of hydrogen. I'm going to write H2 because hydrogen is a diatomic element. So here we have hydrogen and water mixed together, but hydrogen is not, the hydrogen we're looking at here is not in a compound with the water. So one thing that gets confusing about these diatomic elements is when do you put the 2 there and when do you not put the 2 there? if you're doing a chemical reaction or calculating a molar mass of an element by itself, like hydrogen, then we're going to put the 2 there. If we've got something like hydrochloric acid, where the hydrogen and the chlorine are together, hydrogen doesn't need one of her little friends because she has chlorine to hang out with, right? So if a diatomic element is part of a compound, you don't need the 2, but we do need the 2 here. So the mass then, 0.00596668 moles, and to find grams, I'm going to multiply by grams per mole. But then I need to do one more conversion factor, right? I need to get to milligrams. So I'm going to multiply by milligrams and divide by grams. And leave myself no place to answer. So on the periodic table, we see that the molar mass of hydrogen atoms is 1.008. So H2 is 2.016. And over here, milli stands for 10 to the minus 3. So that goes on the other side of the line. 1 milligram is 1 times 10 to the minus 3 grams. And with 3 sig figs, I'm getting 12 milligrams. Any questions? $12 milligrams.